This conference will now be recorded.
Good afternoon all. We will start with our session. So today I'm here to give a demo on design for testability, which is nothing but DFT. So before we go into what is called as design for testability DFT, we'll first try to understand what is VLSI. So VLSI stands for Very Large Scale Integration. VLSI stands for Very Large Scale Integration. Very large scale integration. So VLSI means implementation of million transistors in a small area. That is what is called as VLSI. Implementation of million transistors in a small area. Okay. And goal of VLSI. Goal of VLSI means if a particular company, if they are designing a chip, then they will be having some primary conditions or primary targets that has to be met. That is what is the goal of VLSI. So the goal of VLSI is, first one is high performance. Second one is low power. So we will be going for low power design in order to achieve longer battery life. To achieve longer battery life. And then low area. So if our chip size is small, then our product size will also be small. So that's why we will be going for low area design. Okay. Suppose if our chip size is huge, then our product size will also be huge. So that is why we will be going for low area design. Okay. And then this is how our chip will look after manufacturing. So after manufacturing, this is how our chip will be looking. And then next we will see about ASIC. The full form of ASIC is Application Specific Integrated Circuit. So this is the full form of ASIC. Application Specific Integrated Circuit means the IC which we are designing, the chip which we are designing, it will be specific to a particular application. The chip IC which we are designing, it will be specific to a particular application. So say for example, a modem chip. A modem chip, it cannot be used as a chip which is responsible for deployment of airbag in your automobile. So that is why it is called as application specific integrated circuit. The IC which we are designing, the chip which we are designing, it will be specific to a particular application. Okay. So application specific integrated circuit, the chip which we are designing, the IC which we are designing, it will be specific to a particular application. As I told, a modem chip, it cannot be used as a chip which is responsible for deployment of airbag in your automobile. And ASIC flow means it gives the steps which we need to follow for designing a chip. So these are all the steps which is involved in the process of chip design. That is what is ASIC flow. It gives the steps which we need to follow for designing a chip. It gives the steps which is involved in the process of chip design. So in the next slide, we will discuss the various steps which is there in the ASIC flow, various stages which is there in the ASIC flow. Okay. So the first one is nothing but the design specification stage. So design specification stage, what will happen is, based on the application for which we are designing the chip, certain specifications will be decided, like what has to be the speed, how many memory modules are required, how many processors are required, how many sensors are required, what has to be the power. So such kind of specifications will be decided. Okay, so in the design specification stage, what will happen is, based on the application for which we are designing the chip, based on the application for which we are designing the chip, certain specifications will be decided, like what has to be the speed, and then how many memory modules are required, how many memory modules, okay, how many memory modules, and then processors, okay, and then sensors are required, and what has to be the power. So such kind of specifications will be decided. Now after the design specification stage, we have the design code stage. So the design code will actually be written by the design team. So they actually describe the functionality of the chip. They write the design code of the chip. And the design code, whatever is written here, it will be in behavioral model or data flow level model. Okay, so it will be in behavioral model or means in data flow level data flow level. So the design code will be written by the design team. They will be describing the functionality of the chip. So the design code, it will be written in behavioral model or data flow level model. Now after the design code stage, we have the verification stage. Verification team, they validate the functionality of a design to ensure that it meets the required specification and performs as intended. They will be validating the functionality of the design. Validate the functionality of a design to ensure that it meets the required specification. It meets the required specification and performs as intended. Performs as intended. Now after the verification team, we will be having the synthesis. So during synthesis, what will happen is the behavioral and data flow level model code, it will be converted into a structural form, or we can call it as a technology node specific gate level netlist. Okay, so the behavioral and data flow level model code, the behavioral and data flow level model code, it will be converted into structural form. It will be converted into structural form, or we can call it as a technology node specific gate level netlist. Technology node specific gate level netlist. And after the synthesis team, we will be having the design for test team, DFT team. DFT team, what do we do is we actually insert some test structures into the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. We'll try to understand about what is this design for testing in detail during our upcoming slides. Now after the design for test team, we have the physical design team. So physical design team, they actually convert the gate level design into layout form. Okay. So physical design team, they convert the gate level design into layout form. Convert the gate level design. Gate level design into layout form. Okay. And then after this, we have the sign off. So during sign off, we do these things. So STA, PV, and then LEC. So all these things will be performed at the time of sign off. Okay. So like STA. So the full form of STA is static timing analysis. So that is what is the full form of STA, static timing analysis. So as its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violation. Full form of STA is static timing analysis. As its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violations. Okay, and next is physical verification. PV stands for physical verification. Physical verification is actually to verify the layout of the circuits. And then the next one is LEC. Full form of LEC is logical equivalence check. Logical equivalence check (LEC) is done to check whether the final design is logically equivalent to the original design or not. And why it is actually done is because if you see in the process of our chip design, in each and every stage, it actually undergoes a lot of changes. So first, during the design code stage, the behavioral and data flow level model code was written, and later at the time of synthesis it was converted into a structural form, that is, it was converted into a technology node specific gate level netlist. And if you are going for low power design, then some more new cells will be, some more special cells will be added, like isolation cell, retention registers, clock gating, like that. Some more new cells also will be added into your design. And then DFT team, we have DFT team. We will be adding our own test structures into the design, like scan insertion, embed insertion, boundary scan insertion, like that. We will be adding our own test structures into the design. And after this, we had the physical design team, where the gate level design was converted into layout form. So if you see, in each and every stage, our design is undergoing a lot of changes. So that's why logical equivalence check (LEC) is done to check whether the final design is logically equivalent to the original design or not. Actually, LEC will be done after every stage, that is after synthesis, after DFT, after PD, like that. After every stage, LEC will be performed. And then finally, you have the tape out. So tape out is nothing but delivering the database to the manufacturing unit. So that is what is tape out, delivering the database to the manufacturing unit. So delivering the database to the manufacturing unit. Okay, so that is what is tape out. Okay, and finally we have this packaging and testing. So packaging and testing, it is actually done after manufacturing. Packaging and testing is done after manufacturing. So what is called as packaging? So basically, this is how your chip will look like. This complete circle is your wafer, and each small portion is called as a die. So covering this die with a protective layer, that is what is called as packaging. And testing is actually done to check whether our chip is good or not, whether our chip has any manufacturing defects or not. So that is what is testing. So this packaging and testing, it is done after manufacturing. So packaging means covering this die with a protective layer is called as packaging. And testing is actually to test whether our chip is good or not, whether our chip has any manufacturing defects or not. Okay. So in our upcoming slides, we will try to discuss more in depth about the design for testing and also regarding this testing, okay, in detail in our upcoming slides. So now let's try to understand what is DFT, design for testability. So as I told in the previous slide, DFT, it is to insert test structures into the design during the pre-silicon stage. Pre-silicon stage means before manufacturing. Pre-silicon stage is before manufacturing. Okay? Pre-silicon stage means before manufacturing. So to facilitate detection of manufacturing defects in the chip, which means to help in the detection of manufacturing defects in the chip. So we will be adding our own test structures into the design, like scan insertion, embossed insertion, boundary scan insertion. Like that, we will be adding our own test structures in the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip, to help in the detection of manufacturing defects in the chip. Okay? So, if suppose a particular chip fails after manufacturing, if suppose a particular chip a particular chip fails after manufacturing, fails after manufacturing, DFT engineers will be able to tell will be able to tell what manufacturing defect what manufacturing defect has caused the chip to fail, caused the chip to fail. Okay, so if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail, what manufacturing defect has caused the chip to fail. Okay? So DFT team, we will be adding our own test structures into the design, like scan insertion, embossed insertion, boundary scan insertion, like that, during the pre-silicon stage, to facilitate the detection of manufacturing defects in the chip, to help in the detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. And what is the role of DFT engineers? So as I told in the previous slide, DFT is to insert test structures in the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. As I had told in the previous slide, the same point is replicated here, written over here. DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. Okay, DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. So let's try to understand this point with the help of an example. We'll take an example and we'll try to understand this. That's okay. So yeah, we'll take an example and we'll try to understand this. So say for example, this is the half-adder design. What should be the half-adder design? Sum is A XOR B, carry will be AB. So this is what is the equation for a half-adder. Now whether this is written correct or not, sum is equal to A XOR B, carry is equal to AB, whether whatever is written here, whether this is correct or not, that is what will be checked by the functional verification team. So in the ASIC flow, we also had a team called as the verification team, right? So this is what will be checked by the functional verification team. They will be checking the functionality. So by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, this will not function like a half adder. Okay, this will not function like a half adder. So this is what will be checked by the functional verification team. They will be checking the functionality. Now DFT team, we do not check the functionality. We check whether each and every net of the half adder is free of defects or not. So for example, this is our intended design. So A XOR with B, A and with B. So A XOR with B is sum, A AND with B is carry. So A and B inputs of these gates, it is coming from some flops, and output of these gates, it is going to some flops. So this is what is our intended design. Now suppose during manufacturing, unintentionally during manufacturing, A net of this AND gate got connected to ground. So these kind of things will only be checked by the DFT team. So DFT team, we do not check the functionality. We check whether each and every net of the half adder is free of defects or not in this example. So this is the intended design of our half adder. Now during manufacturing, unintentionally during manufacturing, say for example, A net of this AND gate got connected to ground. So these kind of things only will be checked by the DFT team. So in this example, DFT team will check whether each and every net of this half adder is free of manufacturing defects or not. Okay, so these kind of things is what will be checked by the DFT team. So when we do the regular course, that is at 3.5 months DFT course, when we do DFT advanced course, when we do, so at that time we will give you some more examples and tell you the differences between the DFT engineer and functional verification engineer. We will also explain why do we need a DFT engineer when functional verification team is there, and why do we need a functional verification team when a DFT team is there. So all those things we will try to discuss it more in detail during our regular course. With the help of various examples, we will try to understand everything. Okay, so as of now, I've just given an overview about what is the difference between functional verification team and DFT team. We will discuss it more in detail about the differences between the functional verification team and DFT team's tasks, and we will also try to understand why do we need to have both the teams. Okay, why do we need to have both DFT team and functional team? Why do we need to have? Okay, so we will try to understand that more in detail when we do the original course. When we will try to understand these points in detail. So now let's focus on testing. So as we saw in the ASIC flow, so after manufacturing there was a process called as testing in the ASIC flow slide, as we have seen. So this testing, it is actually done after manufacturing. So testing is a process of determining whether a device is good or not. Okay, testing is a process of determining whether a device is good or not. Testing, it actually includes test pattern generation, application, and output evaluation. So basically these test patterns, it will be generated by the DFT engineer. Before manufacturing itself, will be generating the test pattern. So it will be consisting of the input sequence and then the expected output. It will be consisting of the input sequence and then the expected output. Now what will happen is, at the time of testing, this input sequence will be applied onto the chip. And then the output of the chip, it will be compared with the expected output. Now if the output of the chip, if it is equal to the expected output, it means that the chip is good. There are no manufacturing defects in the chip. Output of the chip, if it is not equal to the expected output, it means that the chip has failed. There are some manufacturing defects in the chip. Okay? So at the time of testing, what will happen is, testing includes test pattern generation, application, and output evaluation. So these test patterns, it will be generated by the DFT engineers. Before manufacturing, it will generate the test patterns. It will be consisting of input sequence and then the expected output. It will be consisting of input sequence and then expected output. So now what will happen? This input sequence will be applied onto our chip, and then the output of the chip, it will be compared with the expected output. If the output of the chip, if it is equal to the expected output, it means that the chip is good. So there are no manufacturing defects. If output of the chip is not equal to the expected output, it means that the chip has failed. There are some manufacturing defects in the chip. Okay, if output of the chip, if it is not equal to the expected output, it means that the chip has failed. There are some manufacturing defects in the chip. Now, if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. If a particular chip fails, DFT team will be able to tell what manufacturing defect has caused the chip to fail. Now, possible outcomes of testing, there are basically four possible outcomes of testing. So, good IC means it has to pass the test. So, if a good IC, if it passes the test, then it is called as true pass. It is called as true pass. Good IC means it has to pass the test. If a good IC, if it passes the test, it is called as true pass. Now, if a defective IC means it has to fail the test. So, if a defective IC, if it fails the test, defective IC, if it fails the test, it is called as true reject. Defective IC means it has to fail the test. So, if a defective IC, if it fails the test, then it is called as true reject. Now, if a defective IC, if a defective IC, okay, if a defective IC, if it passes the test, if suppose the defective IC, if it passes the test, then it is called as test escape. It is also called as under testing. Defective IC, if it passes the test, it is called as test escape. It is also called as under testing. And if a good IC, if it fails the test, a good IC, if it fails the test, it is called as yield loss. It is also called as over testing. If a good IC, if it fails the test, it is called as yield loss. It is also called as over testing. So, goal of good testing is actually to reduce the test escape and yield loss. Goal of good testing is actually to reduce the test escape and yield loss. Now, what is called as yield? Yield means number of good chips divided by the total number of chips. So, out of a total number of chips which is manufactured, how many chips are good? So, that is what is called as yield. Number of good chips divided by the total number of chips. So, now we will try to understand what are called as manufacturing defects. Manufacturing defects are the defects that are caused due to process variations and random imperfections. So, process variations means slight variation in the transistor channel length, metal interconnect width and thickness. All those things will impact the logical and timing performance. And random imperfections means it can result in unintentional shorts, unintentional opens. So, that is what is called as random imperfections. Now, we'll try to understand the flow of DFT. So, first we have the insertion. So, insertion means we will be adding the extra logic. So, as we saw, DFT, we will be adding our test structures into the design, like scan insertion, embedded insertion, boundary scan insertion, like that. That adding of that extra logic is what is called as insertion. And after that, we have the generation step where the patterns will be generated. So, the patterns, it will be consisting of the input data and then the expected output. Okay, during the generation step, patterns will be generated. So, the patterns will be consisting of the input data and then the expected output. Okay, and then finally we have the validation, which is nothing but the simulation. So, we'll try to understand about this in detail in our upcoming slides as well. So, in the upcoming slides, we will try to see a course overview. So, what are all the topics which will be covered in our course, and we will also try to have a short overview on each topic, and we will also see what are all the subtopics which will be covered as a part of each topic. So, the first one is scan insertion. We'll first start with the scan insertion. Then we will be having the scan compression, and after that we have on-chip clock controller OCC, then automatic test pattern generation ATPG, then simulations, then JTAG joint test action group. So this JTAG is a IEEE 1149.1 standard. IEEE 1149.1 standard, and then we have MBIST, memory test. Okay, and we also have boundary scan. Okay, so we will also be covering IJTAG as a part of our course. So it is nothing but IEEE 1687 standard. This is nothing but IEEE 1687 standard. Okay, so I have not written about it in our demo session, in our overview class, because in order to understand about IJTAG you need to understand JTAG fully. So that's why I have not included IJTAG in our demo session, but we will also be covering IJTAG, so which is nothing but the 1687 standard. Okay, so now this is what is our course outline for theory topics. These are all for the theory topics. What will be covered in our labs, I will tell that after completing the theory course outline. After completing it, we will see what will be covered in the lab sessions also, and how our lab test cases are structured. So now we'll just try to have a overview. So like whatever topics we have written in our course outline, we'll just try to understand what is it and why it is required. We'll try to understand. Okay, so the first one is scan insertion. So before we go into it, let me once check the chat box if any questions are there till this point. uh, okay, so am I audible? Is my voice clear, or is my voice breaking? Is it clear? Am I audible?
Yeah, now you are audible.
Okay. So like when I'm presenting, like I'll not be able to see the chat box. So if in case any audio or video issue is there, please you can unmute yourself and let me know. I'll check that. So now let's continue. So the first topic in our course is scan insertion. So during scan insertion, what will happen is the normal flops in the design, it will be converted to a scan flop. The normal flops in the design will be converted to scan flops, and these scan flops will be stitched into a scan chain. So this is what is scan insertion. All the normal flops in the design, it will be converted to scan flops, and those scan flops, it will be stitched into scan chains. This is what we call it as scan insertion. So what is a scan flop? What is the scan flop? How it functions? And what is the scan chain? How it functions? All those things we'll try to understand it when we do the appropriate topic. When we do the regular course, we will try to understand. Okay, so what is a scan flop? What is its functionality? What is a scan chain and how it functions? We'll try to understand it in detail during our course. So as of now, just understand that during scan insertion, all the normal flops in the design will be converted to scan flops. And these scan flops, they will be stitched into a scan chain. These scan flops will be stitched into a scan chain. Okay. So now why do we need to go for scan insertion? Why do we have to convert the normal flops into scan flops? And why do we need to stitch the scan flops into a scan chain? Why do we need to do all these things? We'll try to understand. So what is the need of scan insertion? Why do we need to convert all the normal flops to scan flops, and why do we need to stitch the scan flops into a scan chain? Why do we need to do that? So we'll try to understand. We need to go for scan insertion in order to gain controllability and observability of the design. So which means in order to easily control and observe our design. In order to easily control and observe our design, we need to go for scan insertion. Okay, we need to go for scan insertion in order to gain controllability and observability of the design, which means in order to easily control and observe our design. We'll try to understand this point with the help of an example. So say for example in my design, I'm having a 10-bit counter. I'm having a counter initialization and a counter observation circuit as well. Now suppose the counter is failing. That is after counting 999, instead of counting 1000, it is again counting 999. That's why the counter is failing. So how many clock pulses it will be required by the functional verification team and DFT team to find out that the counter is failing? Let's try to understand. Okay, so we are just trying to understand the need of scan insertion by taking a small design. So in my design, I have considered a 10-bit counter, a counter initialization circuit and a counter observation circuit. Now suppose the counter is failing. So after counting 999, instead of counting 1000, it is again counting 999. So how many clock pulses will be required by the functional verification team and DFT team to find out that the counter is failing? We'll try to understand. So functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Okay. So we'll try to understand why. So as we discussed earlier, functional verification team, they will be checking the functionality. Functional verification team, they check the functionality. Okay. So they check the functionality. Okay. So functionality means they will check whether, in this example, they will check whether the counter properly counts from 0 to 1023. Okay, they will be checking the functionality. That is, in this case, they check whether the counter properly counts from 0 to 1023. Now here in this case, counter, it is failing at the 1000th pulse. Counter is failing at the 1000th pulse. Okay, so that is why 1000 pulses are required for this. 1000 pulses are required. And then some more clock pulses will be required for counter initialization and counter observation. Some more clock pulses. Some more clock pulses will be required for counter initialization and counter observation. So counter initialization is they have to bring the counter to the initial state. And counter observation is the output of the counter. It has to be taken to some register and the register has to be read. So some more clock pulses will be required for counter initialization and counter observation. So ultimately, functional verification team required more than 1000 clock pulses, to detect that the counter is failing in this case. Okay, so we had a team called as a verification team in the ASIC flow, right? So functional verification team, they required more than 1000 clock pulses to detect that the counter is failing in this example. Now coming to the DFT team. DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. Range of 100 clock pulses means it will be somewhere around like 80, 90, 100, 120, 200, etc. In the range of 100 clock pulses, we'll be able to tell that the counter is failing. And how DFT team is able to tell that? How we are able to tell that how DFT team is able to tell that the count is failing approximately in the range of 100 clock pulses? It is because DFT team, we are going for scan insertion. We have gone for scan insertion. So that's why we are easily able to load the appropriate sequence into our design. That is, we are easily able to control and observe our circuit. DFT team, we are going for scan insertion. So that's why we will be easily able to control and observe our circuit. We'll try to understand this point. In order to understand how DFT team will be able to tell that the count is spinning approximately in the range of 100 clock pulses. In order to tell that, you first need to understand what is a scan cell, what is a scan chain, how a scan chain operates, and then only then you will be able to tell this point. So that's why we will discuss it during our main course. When we do the regular course, we will try to understand this. Okay, we'll take up the same example once again. We will explore it and we will see in detail how DFT team we are able to tell that the counter is failing approximately in the range of 100 clock pulses itself. Okay, so as of now, just remember that it is because DFT team we are going for the scan insertion, because of which we are easily able to control and observe our circuit. Okay, and if you just compare functional verification team, they required more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, we are able to tell that the counter is failing approximately in the range of 100 clock pulses itself. So DFT team, if you see, we are able to tell that the counter is failing in significantly less number of clock cycles compared to the functional verification team. Okay, and DFT team, we will also be able to tell what manufacturing defect has caused the counter to fail. Even this point you will be able to understand when we do the regular course. When we do, we will be explaining that how DFT team are able to tell what manufacturing defect has caused the counter to fail. So we will be able to give this detail as well, and how we are able to tell that we will discuss it during our regular course. Okay, so this is what happens. This is what is the need of scan insertion. As you can see here in the counter example, DFT team, we are able to tell that the counter is failing in significantly less number of clock cycles as compared to the functional verification team. So that is what is the need of scan insertion. So we are going for scan insertion in order to easily control and observe our circuit. Okay, and as a part of our scan insertion course curriculum, so we'll try to see what are all the topics will be covered, what are all the subtopics will be covered as a part of our scan insertion course. So the first topic in our course will be scan insertion. Topic 1 is scan insertion. Okay. So in the first class, we'll try to understand what is scan cell, what is scan chain, and then we will also try to understand the scan chain operation. Okay, what is scan cell, what is scan chain, and we'll also try to understand the scan chain operation. Then in the next class, in the second class, we'll try to understand the need of scan insertion. Need of scan insertion. So the same counter example, whatever I have told in the previous slide, this one, we will try to take the same example once again and explore the points more in detail with respect to the DFT team, right? The points with respect to DFT team, whatever is written here, we'll try to explore it in more in detail, and we'll try to understand how we are able to give these statements. Okay, so that is what is the need of scan insertion topic. We'll try to explore it more in detail. And we will also see by the end of this topic, you will also be able to understand clearly what is the difference between DFT engineer and functional verification engineer, DFT engineer and functional verification engineer difference. And you will also be able to understand why both the DFT as well as functional verification team are required. So all these things you'll be able to understand when we complete this topic. Okay. Why both the DFT engineer as well as functional verification engineer are required. As well as functional verification engineer. Functional verification engineers are required. Okay. And then in the third class, we will discuss about scan DRCs. What is DRCs? Full form of DRC is design rule checks. Design rule checks. So, what is design rule checks? So, what is scan insertion? Scan insertion means all the normal flops. All the normal flops, they have to be converted into a scan flop. And yes, scan flops, it will be stitched into a scan chain. Yes, correct. But if if it has to be converted to a scan flop, then it has to pass certain rules. It has to pass certain rules. Pass certain rules. Now, what are those rules? That is nothing but your DRCs. That is what is your design rule checks. Okay, so if a normal flop, so during scan insertion, what will happen? The normal flops will be converted to scan flops, and the scan flops will be stitched into a scan chain. So if a normal flop, if it has to be converted to scan flop, then it has to pass certain rules. What are those rules? That rules is what is called as DRCs. Now we will try to understand about the various scan DRCs and why it is required. So there will be various scan DRCs like clock controllability DRC, okay, and then set reset controllability DRC, set reset controllability DRC, okay, and then feedback loop DRC, X source DRC, and then bus contention, bus contention, then potential trace. Likewise, we'll be having various DRCs, various uh, design rule checks would be there. So we will try to understand about these various scan DRCs. We'll try to understand like what clock controllability DRC means, what is it, okay, and in which kind of situation this clock controllability DRC will be violated, and whenever it is violated, what can be done in order to resolve it. So all those things we will try to understand. For each and every DRC, we will try to understand these things. That is what we are going to do it on day 3. Day 3, we are going to work on scan DRCs. We are going to understand the various scan DRCs. Okay. And then after this, next day, what we are going to do is we will be understanding something called as a balancing of scan chains. We'll try to understand what is called as balancing of scan chains. Balancing of scan chains. What is called as balancing of scan chain means keeping almost equal number of flops in all the scan chain is what is called as balancing of scan chains. Keeping almost equal number of flops. Almost equal number of flops in all scan chains. Okay, that is what is called as balancing of scan chains. Balancing of scan chains means keeping almost equal number of flops in all scan chains. And why do we need to go for balancing? Why do we need to go for balancing? We need to go for balancing in order to reduce the test time. In order to reduce the test time. So how, if you go for balancing, you are able to achieve reduction in test time? We will discuss it during our course. We will discuss this during the course on day 4 of our scan insertion topic. We will try to understand. We will discuss during the course. Okay. So this is what in day 4 we will try to understand a concept called as balancing of scan chains. What is balancing of scan chains? Balancing of scan chain means keeping almost equal number of flops in all scan chains. That is what is called as balancing of scan chains. Why we are going for balancing? To reduce the test time. And how, if you go for balancing, you are able to achieve reduction in test time? We will discuss it during our course when we do the balancing of scan chain topic. Now, if you want to achieve balancing, if you want to have almost equal number of flops in all the scan chain, if you want to achieve balancing, then you need to go for certain techniques like edge mixing and domain mixing. Okay, you need to use certain techniques like edge mixing and domain mixing. Okay, in order to achieve balancing. In order to achieve balancing, achieve balancing. Okay, we need to go for edge mixing and domain mixing. Edge mixing and domain mixing. Okay, and what is called as edge mixing, what is called as domain mixing, and why do we need to go for this edge mixing and domain mixing technique in order to achieve balancing? All these things we will try to understand it during the main course, that is during the day 4 of our scan insertion part of our training. We'll try to understand those things. And then in the 5th day, what we'll try to understand is, as we saw, in order to achieve balancing, we need to go for techniques like edge mixing, domain mixing, those things, right? Now, if you go for edge mixing and domain mixing technique, again it will introduce some problems. Now, what are the problems which that edge mixing and domain mixing will cause? And how you can actually overcome those problems? Those points we will try to understand it during the day 5 of our training. Okay, so during the day 5, 5th day, day 5, we'll try to understand the problems in edge mixing and domain mixing. Problems in edge mixing and domain mixing. Edge mixing and domain mixing. Okay, and how to resolve them. How to resolve them. So all these things we'll try to understand it on the day 5 of our training. And then on the day 6 of our scan insertion class, we'll try to understand some small definition type of topics. Definition type topics. Like we'll try to understand what are the different types of scan cells, and then what is scan chain reordering, and then like what are the benefits of scan, like that we'll try to see some small definition type of topics. So all these things will be covered as a part of our scan insertion. So now I'm talking only with respect to the theory part. So in labs we'll try to see later what are the things will be covered in our labs. We will try to understand it later. So now these are all the topics which will be covered in the scan insertion theory. After completing the theory course overview, I'll also give you an overview about what all the things will be covered in the labs. So this is what is the first topic, and these are all the subtopics which we will be covering it as a part of our scan insertion course. Okay. And before we go into the next topic, let me once check the chat box and see if any questions are there. Okay, I'll just okay. Let me just try to uh, check that once. The audio issue. Just a second. Okay, let me just try to uh, end the meeting and then once again start the meeting because of audio issue. So can you rejoin the meeting once again? Can anyone confirm whether I'm uh, okay, whether my voice is audible and whether my screen is visible? Can anyone confirm that? Is my voice audible and whether my screen is visible now? Am I audible? Is my screen visible?
Yeah, you are audible and screen also visible.
Okay. So next we will go to the next topic, which is nothing but scan compression. So scan compression means what will happen is a single scan channel is internally divided into multiple scan chains. Or you can tell that the multiple scan chains, they are compressed into external channels. Okay, so the the internal scan chains, internal scan chains will be compressed into external channels. Will be compressed into compressed into external channels. External channels. Okay. So the internal scan chains will be compressed into external channels. That is what is called as scan compression. So these are all your internal scan chains. So say for example you are having like these are all your internal scan chains. Okay. So say for example you are having 100 internal scan chains like scan chain 1, scan chain 2, scan chain 3, it goes on and it goes on till scan chain 100. So say for example you are having 100 internal scan chains. Now during the scan compression topic, what will happen is these internal scan chains, they will be compressed into external channels like this. They will be compressed into external channels. So these are your external channels. This is your external channel and this is also your external channel. Okay, so the internal chains, they are compressed into external channels. Okay. So you can even tell like a single scan channel. The scan channel, if you see, it is internally divided into multiple scan chains. Yes, that is also correct. Or else you can even say that the internal scan chains will be compressed into external channels. That is what is called as scan compression. The internal scan chains will be compressed into external channels. And why do we need to go for scan compression? Why scan compression is required? We'll try to understand. We need to go for scan compression in order to reduce the test time and also to reduce the test data volume. Test data volume means it is the number of bits of pattern. So that is what is test data volume. Number of bits of patterns. Okay. So we need to go for scan compression in order to achieve reduction in test time and reduction in test data volume. Now, how if we go for scan compression, we are able to achieve reduction in test time and reduction in test data volume. We will try to understand logically, and we will also try to understand with the help of formulas. We'll take some formula. We'll take the formula for test time and test data volume. We will substitute values into it, and we'll try to understand with the help of formulas also how with the help of scan compression we are able to achieve reduction in test time and how we are able to achieve reduction in test data volume. Okay. So, so now in order to achieve scan compression, if you are using mental graphics tools, then you need to add up a component called as the EDT component. The full form of EDT component is embedded deterministic test. Embedded deterministic test. Embedded deterministic test. So this is what is the full form of EDT logic. So the full form of EDT logic is embedded deterministic test. If you want to achieve scan compression, if you are making use of mental graphics tools, then you will be adding up a logic called as embedded deterministic test. Now this is what is the component of the EDT logic. So one component is the decompressor logic, another component is the compressor logic. So this is the decompressor. This is the decompressor component. This is the decompressor component. And then this is the compressor, or we can call it as the compactor, compressor component, or else in certain documents it will also be called as the compactor. So these are all the components of EDT logic. So basically there are four components of EDT logic. I have only represented these two components. I have only represented the decompressor and compressor components alone I have represented, but there will be two more components. Total four components are there. So first one is the, as it is given in the picture, the decompressor component, and then the compressor component, and then the controller. We'll be having something called as a controller, and we'll also having the bypass logic. We will also be having the bypass logic. So in order to achieve scan compression, we'll be adding up the, if you're using metagraphics testing tool, you'll be adding up a logic called as EDT. The full form of EDT is embedded deterministic. Yes, you can tell. Yes, you can tell. Somebody had asked something. I wasn't able to hear properly. Can you tell? Like somebody had asked something, right? You can tell. Okay, we'll continue now. Okay. So if you're making use of Mentor graphics tool, then in order to achieve scan compression, you will be adding up a logic called as the EDT logic. The full form of EDT is Embedded Deterministic Test. So inside the EDT logic, you'll be having various components like decompressor, compressor, controller, bypass logic. So likewise, four components will be there as a part of the EDT logic. So in the picture below, I have just represented two components, only the decompressor and compressor components I have represented it. So during our course, we'll try to understand the entire structure of our EDT logic. We will try to understand what is decompressor, what role it plays, what is compressor, what role it plays, what is controller, what is bypass logic. So all those things we will try to understand it when we do the regular course. When we do our original course, at that time we'll try to understand about all these all the components of the EDT logic. What are all its decompressor means what is its structure and what is its functionality. Same way for compressor, same way for controller, same way for bypass logic. We'll try to understand about each and every component in it. Okay. So as a part of our scan compression part of the training, so we'll see what all the things will be covered during our scan compression part of the training. So during day one of our scan compression part of training, we'll try to understand what is scan compression. We'll try to understand what is scan compression. Okay. And then we'll try to understand the need of scan compression. Need of scan compression. So need of scan compression is, as I told in the previous slide, we'll be going for scan compression in order to achieve reduction in test time, reduction in test time, okay, and in order to achieve reduction in test data volume, in order to achieve reduction in test data volume, test data volume. So how if you go for scan compression? Okay, so how if you go for scan compression, you are able to achieve reduction in test time and you are able to achieve reduction in test data volume. How you are actually able to do that? That is what we'll try to understand it with the help of logically also we'll see. Logically also we will explain, and we will also explain with the help of some formulas. We will explain it during our course, both logically and also with the help of formulas. And also with the help of formula. Okay. And we'll also understand about a component or about a quantity called as compression ratio. So basically compression ratio, that quantity is number of internal chains by number of external channels, number of internal chains divided by number of external channels, divided by number of external channels. So this is what is the compression ratio quantity. Compression ratio is number of internal chains divided by number of external channels. We'll also have a discussion about this compression ratio quantity. Okay. And we will also try to understand how to decide the number of internal chains and external channels for a particular design. Okay, so how to decide the number of internal chains. How to decide the number of internal chains and external channels. Okay, and external channels and external channels for a particular design, for a particular project, for a particular project. We'll try to understand that as well. How to decide the number of internal chains and external channels for a particular project. So this is what we will understand it during the first class of our scan compression topic. Then during the second class of our scan compression topic, okay. So in day two, we'll start with the EDT discussion about the EDT logic. As I told, if you are making use of mentor graphics tools, Then in order to achieve scan compression, you will be adding up a logic called as EDT logic. So we will try to understand EDT logic. So we'll first try to understand about the decompressor component. We'll try to understand about the decompressor component. And then in the third day of our scan compression topic, we'll try to understand. Again, we'll have a discussion. So this is part 1 of EDT logic discussion. In day 3, we'll try to have a part 2 of our EDT logic discussion. So where we'll try to understand about the compressor or compactor logic and then the controller logic. Okay, we'll try to understand about the compressor or compactor logic. Compressor logic, it's also called as the compactor logic. And we'll try to understand about the controller logic. Try to understand about the controller logic. Okay. And then in the fourth day of our training, scan compression training, we'll try to again discuss about the EDT logic. So this is like part 3 of our EDT logic discussion, where we will discuss about the bypass logic, plus some more miscellaneous points like pipeline flops in the compressor. Okay, so pipeline flops in the compactor, pipeline flops in compactor, and then like lockup cells in the EDT, lockup cells in EDT. Okay, so like why compression ratio doesn't exceed above 100x, why we usually make sure compression ratio compression ratio doesn't exceed 100x, does not exceed 100x. And then merits and demerits of high and low compression ratio, merits and demerits of high and low compression ratio. Okay, so all these things, all these miscellaneous points, we will try to cover it on the day 4 of our scan compression part of our training. So these are all the topics and subtopics which we will be covering it during the scan compression part of our training. Okay, so scan compression, it is also called as EDT insertion, scan compression or EDT insertion. Okay, so yeah. Okay, because in order to achieve scan compression, you need to insert the logic. EDT logic has to be inserted. So that is why scan compression topic, it can also be called as EDT insertion. So before we move to the next topic, let me just check the chat box once. Okay, then we'll go to the next topic. So the next topic is ATPG. The full form of ATPG is automatic test pattern generation. So this is the full form of ATPG, automatic test pattern generation. As its name suggests, it is a process of generating test patterns for a given fault model. There will be various fault models like stuck at fault model, TDF, PDF, IDDQ, like that there will be various fault models. ATPG, it is actually a process of generating test patterns for a given fault model. Okay. So during ATPG, what will happen? Test patterns will be generated. During ATPG, test patterns will be generated. These test patterns will only be used to test the chip after manufacturing. And after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. And how are we sure that our test patterns will be able to detect most of the manufacturing defects? It is because our tool does a process called as fault simulation in order to generate the test patterns. Okay. So ATPG means it is a process of generating test patterns for a given fault model. So there will be various fault models like StuckCAD, TDF, PDF, IDDQ. There will be various fault models. So ATPG, it is a process of generating test patterns for a given fault model. During ATPG, what will happen? Test patterns will be generated, and these test patterns will only be used to test the chip after manufacturing. And our test patterns, they should be having a capability. What is the capability? After manufacturing, if suppose there are any defects, our test patterns will have the capability, it should have the capability to detect most of the manufacturing defects. And how are we sure that our test patterns will be able to detect most of the manufacturing defects? It is because our tool does a process called as fault simulation to generate the test patterns. Okay. So during the ATPG part of our training, ATPG, like, it is a very vast topic and it is also not a straightforward topic. So it will take some time to understand. So I'll try to see what all the topics we will be covering it during our ATPG part of the training. Okay, so ATPG is a very vast topic and it is also not a straightforward topic, so it will take some time to explain it and also for you to understand. So topic 3 is ATPG. So what are all the things we'll try to cover is, we'll try to see what is ATPG, what is ATPG, and then we'll try to understand fault simulation. Fault simulation we'll try to understand. Okay, so fault simulation is nothing but it is a technique which the ATPG tool does in order to generate the test patterns. Now this fault simulation, it is not a straightforward topic. It will take some time to understand, so we will explain it using various illustrations. We'll try to explain the fault simulation topic. So in order to understand fault simulation topic, it usually takes around 2 days to explain completely. Okay, fault simulation, it actually takes around 2 days to explain fault simulation topic. 2 days dedicatedly we need to focus on fault simulation in order to understand the fault simulation topic, because fault simulation is not a straightforward topic. Okay, so it will take some time to explain and as well as to understand. So dedicatedly we can allot 2 sessions to understand fault simulation alone, and then we will be covering these fault models. So we'll be covering all these fault models. So, okay, stuck at fault model. What is fault modeling also you'll be able to understand. Okay, so there will be various fault models like stuck at fault model, transition delay fault model, that is what is TDF, path delay fault model, that is PDF, and then IDDQ fault model. So all these fault models we will cover. So this TDF and PDF together, we also call it as the UT speed test. We also call it as UT speed test. UT speed test. All these things we will cover. And we will also cover fault categories. Okay. So what is fault categories? It is nothing but fault dominance, fault dominance, and then fault equivalence, fault equivalence, fault collapse, fault collapse. Okay, so these are the fault categories. And then fault classes. Fault classes, okay, so basically like our faults, they are like broadly classified. Let me write it over there in the other side because I need some space to write it. Okay, so we'll discuss about fault classes. Okay, so basically our faults, it is broadly classified into testable faults, and then Untestable faults. Untestable faults. Again, untestable faults, they are again subclassified into unused, tied, blocked, redundant. Okay. And then testable faults. They are testable faults, they are further classified into detected, possibly detected, ATPG untestable, and then undetected. Again, ADPG untestable means it will again be subclassified into pin constraint, sequential depth, cell constraint, wire, masked primary outputs, etc. Okay. So now, what are each of these things? What is each of these things, and what is all like everything? This complete testable and untestable faults, as well as their subclasses. All those things we will cover it during our topic, during this fault classes topic. So all those things we will cover it, and then we will also try to understand what is called as fault aliasing. Fault aliasing. Okay, and then we'll try to understand what is on chip clock controller, OCC. Okay, what is on chip clock controller, OCC? So we'll try to understand that, and then we will try to understand what is called as coverage, what is test coverage, what is fault coverage, test coverage, and then fault coverage. Okay, and then coverage analysis and improvement. What is coverage analysis, what is coverage improvement, all those things. Coverage analysis and coverage improvement. So coverage analysis and coverage improvement, for in the theory class we'll just give you an overview. We will do this in detail during the labs. In lab class we will do this in detail. Coverage analysis and coverage improvement, we'll do it in detail during the lab class. And we'll also understand what is dead cycles, pipeline to scan enable, test point insertions. Okay, so all those things we'll try to understand it during our ATPG topic. So ATPG topic, it's a very vast topic. So minimum it will take around 6 to 7 sessions minimum. So minimum it will take around 6 to 7 sessions. In some batches it has even taken 10 to 12 sessions also. Okay, so minimum minimum requirement is 6 to 7 sessions minimum it is required in order to cover all these topics in ATPG. And in certain batches, it has even taken 10 to 12 sessions to complete the ATPG topic. Because ATPG, it's not a straightforward topic. It will take some time to understand and explain the concepts. So some batches, it has even taken around 10 to 12 classes. Okay, but minimum requirement is you minimum require around 6 to 7 sessions to cover all the points in the ATPG topic. So this is a very vast topic, okay, ATPG. And then, one second. Then the next topic is simulations. So simulation is actually to validate the patterns which was generated during ATPG. So before we deliver the patterns to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is done using simulation. Simulation, it is actually to validate the patterns which was generated during ATPG. Okay, before we deliver the patterns to test the chip after manufacturing, We need to validate once whether proper patterns are generated or not. And that is what we are validating it with the help of simulations. Okay. And simulations, during our simulation part of our training, we'll try to understand why we need simulations. Okay, why we need simulation in detail. We'll try to understand the need of simulations. Okay, and what happens during simulation. What happens in simulation? Happens in simulation. Okay, we'll try to understand like what is parallel simulation, what is serial simulation, all those things we'll try to understand. Parallel simulation and then serial simulation, what are all those things you will see. And we can also perform simulation by making use of QuestaSim tool, performing simulations using QuestaSim tool. Okay, and like reasons for getting simulation mismatches. Okay, what are all the reasons for getting simulation mismatches? How to debug the simulation mismatches? Okay, simulation mismatch debug. Okay, all those things. So all these topics we will try to understand it during our simulation part of our training. So simulation topic, it will be covered by theory, and labs will be doing it parallelly, and will be covering the uh, simulation topic. So theory and labs will be done parallel, will be done parallel. Okay, so which means theory concept of simulations, the concept of simulations, we will explain it by practically demonstrating and showing in the labs. So that is why for the simulation topic, theory and labs will be done parallelly. Okay, theory and lab sessions will be done parallelly. We'll be explaining the concepts in simulations. We'll be showing what is simulation and what happens in simulation, all those things by practically demonstrating it in the labs. So that is why theory and labs will be done parallelly for the simulation topic. And basically for simulations, you'll be having two simulations. So one is the no timing simulation. One will be the no timing simulation, and the other one will be the timing simulation. Other one will be the timing simulation. So in our course, we will be covering only no timing simulation. Only no timing simulation is covered in our course. Why? Because in order to do timing simulation, you actually require a file, which is nothing but the SDF file. Standard delay format SDF file will be required in order to perform timing simulations. But that SDF file is not available in our institute. So that is why timing simulations, it is not covered currently as a part of our course curriculum. So this is not covered in our course. Okay. So like if in case you want to learn timing simulations as well, if you want exposure in timing simulations also, you can contact Srinivasa sir and see. So if possible, then sir will try to arrange for that SDF file, and also like sir will try to arrange some training on timing simulations as well. Okay, if possible, then sir will try to arrange it. But as of now, we only cover no timing simulation in our course curriculum. Okay, so before we go into the next topic, I'll just check once the chat box. Okay, and next one is JTAG. So the full form of JTAG is Joint Test Action Group. So it is an IEEE 1149.1 standard. Okay, JTAG is Joint Test Action Group. It is a IEEE 1149.1 standard. So why do we need JTAG? Why do we need JTAG? Is it is actually to minimize the number of ports from the top level and also to achieve boundary scan. Okay, we are using JTAG in order to minimize the number of ports from top level and also to achieve boundary scan. Let's try to understand this point with the help of an example. So here if you see, I have kept a list of some important signals. So this memory bypass enable, EDT bypass enable, int mode, X mode, intel test enable, extend test enable. I have kept some signals, right? So these are some important signals. I just kept a list of some important signals. There will be many more signals like this. Okay, I have just kept a list of some important signals. There will be many more signals like this. Now, if all these signals are to be controlled from the top level, that is, if you allocate a top level port to control this memory bypass enable, you're allocating a top level port to control this EDT bypass enable, to control this int mode, X mode, intel testable, extel testable, and there will be many more signals like this. I have just shown a list of some important signals. There will be many more signals like this. Now, if all these signals are to be controlled from the top level, that is, if you allocate a top level port in order to control each and every signal, then what will happen? The number of top level ports, it will increase drastically. Number of top level ports will increase drastically. So that is why we make use of JTAG in order to internally control the static signals. We'll be making use of JTAG to internally control these static signals. Okay, so that is the reason why we are able to minimize the number of ports from the top level. That is the reason why we are able to minimize the number of ports from the top level. Okay, so here in this example, I've kept a list of some important DFT signals. There will be many more signals like this. Now, if all these signals are to be controlled from the top level, that is, if you allocate a top level port in order to control each and every signal, then what will happen? The number of ports from the top level, it will increase drastically. Okay, it will increase drastically. So that's why we make use of JTAG in order to internally control the static signals. And that's the reason why we are able to minimize the number of ports from the top level. So as a part of our JTAG part of our training, we'll first try to understand like JTAG tap architecture. What is JTAG tap? What is JTAG tap architecture? And then like JTAG FSM. Okay, JTAG FSM. Okay. And we'll also try to understand how with the help of JTAG we are able to minimize the number of ports from top level. That is how with the help of JTAG we are able to internally control the static signals. Okay, and that we are able to be with the help of JTAG we are internally controlling the static signals. So that's why we are able to minimize the number of ports from the top level. That is what, while understanding this various states in the JTAG FSM as well as the JTAG tap architecture, while we are discussing it, simultaneously we will also try to understand how with the help of JTAG you are able to internally control the static signals and how with the help of JTAG you are able to minimize the number of ports from the top level. We'll try to understand it how simultaneously when we are understanding the JTAG tap architecture as well as the JTAG FSM. Okay. And then with the help of JTAG, we will also be able to achieve boundary scan. Now, how with the help of JTAG you are able to achieve boundary scan, that also we'll discuss it during our course. Okay, when we do the course, original course, you'll be able to understand how with the help of JTAG you are able to achieve boundary scan. Okay. Now, as of now, we'll just try to understand what is called as boundary scan. So here I have taken a design. So chip 1, chip 2, chip 3 are properly passing the test of DFT, but still the board is failing. Okay, so which means what will happen is after manufacturing, after manufacturing, okay, so first what will happen is chips will be manufactured. Chips will be manufactured, okay, and then after this, the chips will be tested on the AT, that is on the tester. Chips will be tested on the AT, that is on the tester. ATE, or we call it as the tester. Okay, so the full form of ATE is automatic test equipment. Okay. So now what will happen is, this is your ATE. This is how the chips will be tested. So in our example, we are having these three chips, right? Chip 1, chip 2, chip 3. This is chip 1, then this is chip 2, and then this is chip 3. So what will happen? Input of the chip, it will be coming from the AT. Output of the chip, it will be going back again to the AT. Same way in all these three chips. Now what will happen? Chip 1, chip 2, chip 3, they have passed their test on ATE. Okay, chip 1, chip 2, chip 3, they have passed their test on ATE. They have passed their test on ATE. Okay. So which means, as we saw in the first slides, during the testing slide we had seen, right? Passed the test on AT means output of the chip. Output of chip, it is equal to the expected output. Output of chip is equal to the expected output. Okay. Then what does it imply? If chip 1, chip 2, chip 3, they have passed their test on AT, it implies that they are not having any manufacturing defects. They are not having any manufacturing defects. Okay. And after this what will happen? Chips will be placed on the board, PCB board. Okay, chips will be placed on board, PCB board. After this, chips will be placed on the PCB board like this. This is your PCB board. Okay, so this is what is it? Chip 1, chip 2, chip 3. And then the interconnection between the chips and all will be formed like this. Okay. Now, after this, what is happening? Board is tested. Board is tested and it is failing. Board is tested and it is failing. Suppose. Now, chip 1, chip 2, chip 3. Chip 1, chip 2, chip 3, they are internally not having any manufacturing defects because they have already passed their test on AT. As we saw above, chip 1, chip 2, chip 3, they have passed their test on AT, which means they are internally not having any manufacturing defects. Then why is the board, when the board is being tested, why is it failing? It can be due to the manufacturing defects in the interconnection between the two chips. Okay, so this can be due to the manufacturing defects in the interconnection between the two chips. The interconnection between the two chips. So this is where we go for the boundary scan. Boundary scan is actually to test the interconnection between the two chips. Test the interconnection between the two chips. And boundary scan, we will only be covering the theory part because in our institute we don't have the license for boundary scan. So boundary scan we will only be covering theoretically. Okay. So now, as a part of our boundary scan topic, what all the topics will be covered is, we will try to understand what is the structure of boundary scan cell. Okay, boundary scan cell structure. Okay, boundary scan cells structure, and then We'll try to understand the modes of operation of boundary scan cell. Modes of operation of boundary scan cell. Okay, and then we'll also try to understand about the mandatory JTAG instructions. Mandatory JTAG instructions, like what is sample preload, and then X test, and then bypass. Okay, so all those things we'll try to understand. So these are all the things which we'll be covering it as a part of our boundary scan part of our training. Okay, and here we cover only theory part because we don't have the license to do the boundary scan in our institute, so that's why we'll be covering only the theory part for this boundary scan. And apart from this, we will also be covering IEEE 1687 standard, which is nothing but IJTAG. IEEE 1687 standard IJTAG. Okay, we'll try to understand what is the architecture. Okay, and then we will try to understand the comparison between JTAG and IJTAG. We'll try to see the comparison between JTAG and IJTAG. Okay, and we will also try to understand the advantages of IJTAG. We'll also try to understand the advantages of IJTAG. So in order to cover this IJTAG, it will take one session, and in order to cover this JTAG and boundary scan, JTAG and boundary scan, JTAG and boundary scan, it will take one session. Okay, to total two sessions. In order to cover JTAG and boundary scan, it will take one session, and in order to cover this IJTAG, it will take one session. Okay, and these are all the things which will be covering it as a part of our course curriculum. And the next one is MBIST. So the full form of MBIST is memory built-in self-test. Memory built-in self-test. So that is what is the full form of MBIST. So we use MBIST technique in order to test the memories. As its name suggests, memory built-in self-test. So we actually make use of MBIST technique in order to test the memories. So during our MBIST course, what we'll be doing is, in our first day, we'll try to understand the various memory fault models. We'll try to understand the various memory fault models. Memory fault models. Okay, like stuck at trap fault model, transition fault model, address decoder fault model, coupling fault model, like that. Okay, we'll try to understand the various memory fault models, like stuck at fault model, transition fault model, address decoder fault, coupling fault, like that. The various memory fault models, we'll try to understand it during the first day of our training. And then we'll also try to understand, like uh, what is it, we will be making use of algorithms, generalized algorithms, in order to test the memories. So now we will try to understand some basic algorithms. We will try to understand it. We will try to understand some basic memory algorithms. Okay, like 0 1 algorithm, and then checkerboard algorithm, and then MATS algorithm, then MATS plus, then MATS plus plus, like that. And then Marchex, March C, all those things. And these all come under the March algorithms. All these things come under the March algorithms. All these things we'll try to understand. Okay. So now in all these things, what we will understand it, we'll understand what is the sequence of each algorithm. So each algorithm will be having a sequence. What is the sequence of each algorithm? Sequence of algorithm will be able to understand, and we'll also try to understand which algorithm will be able to cover which faults in the memories. Okay, which algorithm will be able to cover, be able to cover which faults in memories and why. Which faults in memories and how it is able to cover it. All these things we'll try to understand. Which algorithm will be able to cover which faults in memories and how. So all those things we'll try to understand. So this completely we'll do it in the day one part of our MBIS training, and during the day two part of our MBIS training, we will try to understand Tessent MBIST. So if you want to implement MBIST using Tessent tools, so what all the things will be there. So that is what is Tessent MBIST. Okay, so we'll try to understand Tessent MBIST implementation. Okay, Tessent MBIST implementation, and then Tessent MBIST architecture. Okay, and then Tessent MBIST operation protocol. Okay, and then we'll try to understand about the grouping of memories. We'll try to understand about the step concept. There is a concept called as step concept, so we'll try to understand all these things. We'll try to understand during the day two part of our training. Okay. And this is regarding our theory part. So in the theory we'll be discussing all these topics. Okay, and now before we go into the lab part of our, what all the things will be covered in our lab portion, let me once check the chat box. Okay, okay, so yeah, now let me give you an overview about what are all the things will be covered in our labs. Okay, so in our labs we'll be covering IJTag insertions, MBIST insertions, scan insertions. So basically there are two approaches. One will be the top down and the other one will be the hierarchical scan. So we will understand both the things, and what is so EDT and OCC insertion, ATPG pattern generation, ATPG and MBIS simulations. So all those things we will cover it. And as I told, simulations will be covering only the no timing simulations. Only no timing simulations will be covered. Okay. So in our course we'll be covering only no timing simulations. If you why timing simulations is not covered is because the SDF file, standard delay format file, is not available in our institute for our test cases. So that's why we don't cover the timing simulations. But if in case you want to get some training exposure on timing simulations as well, you can just contact Srinivasa sir and see. If possible, then sir will arrange for the SDF file and also for some training on timing simulations. So if possible, sir will arrange it. You can just talk with sir and see, discuss it with sir and see. But as of now in our course curriculum we will be covering only the no timing simulations. And also boundary scan also we will only be covering theoretically. We will not be covering the practicals of boundary scan because we don't have the license to do the boundary scan. Okay. And yeah, basically our labs, it is divided into 4 levels. So level 1, level 2, level 3, level 4. Level 1 and level 2 projects, they are like simple test cases. So complexity will be less, like around maximum of 100 flops would be there. These are simple test cases. These are like simple test cases. Complexity will be less. Okay, in level 1 and level 2 projects. Okay, these two things. So in level 1 projects, we are totally having 11 test cases. For these 11 test cases, we will perform the scan insertions. Okay. So basically, like total 11 test cases are there, right? Among which two test cases will be to familiarize yourself with the flow. Two test cases will be to familiarize yourself with the flow. Familiarize with the flow. Okay, two test cases will be to familiarize yourself with the flow. So flow means, like, say for example you are implementing scan using descent tool, right? Then there will be some steps which you need to follow for doing the scan insertion. Practically, if you want to implement scan insertion using descent tools, you'll be having various steps. That is what is called as flow of scan insertion. So two test cases, among these 11 test cases, two test cases will be to familiarize yourself with the flow of scan insertion. Okay. The remaining 9 test cases are there, right? So the remaining 9 test cases, what you'll be having is, you'll be having various DRC violations. Okay, so as we discussed, like if you want to convert a normal flop to scan flop, then it has to pass certain rules. So those rules is what is called as DRCs. So there will be various DRC violations, and how to resolve it also we will be seeing. So in the remaining 9 test cases, each test case will be having a DRC violation. Okay, each test case will be having some DRC violation. We'll try to analyze that DRC violation in the schematic, and we will try to fix the DRC violation. Basically, in order to fix the DRC violation, you can go for 3 methods. You are having 3 methods to fix the DRC violation. 3 methods to fix the DRC violation. Okay. So one will be the manual editing of netlist method. Manual editing of netlist method. Okay. And then the other one will be to autofix method. And then, like, you can make use of certain commands like create instance, delete connection, create instance, delete connection, create connection. Using these commands also you can clear the DRCs. Now, we will cover all the 3 methods with which you can fix the DRC. We will also show you a comparison between each method, okay, and which one is more advantageous, which one you have to give the first preference, which one you can give the second preference, which is more error prone, which is not error prone. So all those things we will understand. We'll give you an overview about all these points as well during our scan insertion labs. Okay. So this is what is our level 1 projects. Now in the level 2 projects, what we will do is, for the same 11 test cases, we will do the EDT insertion. We'll do the EDT insertion, and we will also work on ATPG. So in ATPG, we are going to generate patterns for all these fault models. TUCAT, TDF and IDDQ fault model will be generating the patterns. And as I told, mainly we will be working on coverage analysis and coverage improvement in our labs. Okay, coverage analysis, coverage improvement. Okay, coverage analysis plus improvement, analysis plus improvement we'll be doing. That is the main thing which we'll be focusing in our labs. Okay, in theory class, coverage analysis and improvement will just give you an overview, but in the lab class, we'll practically do it. Mainly, we'll be focusing on coverage analysis and improvement in our labs. So what is coverage? Why you are getting the coverage loss? How you can do the coverage analysis? How you can improve the coverage? All those things mainly we'll see it in our labs. And basically, for all these fault models, we'll be generating the pattern. So we will be we'll be doing the pattern generation with DDT as well as bypass patterns. Both the set of patterns we will generate it. Okay, patterns will be generated with TDT and bypass patterns. Patterns generated with TDT, with EDT, and we'll also generate the bypass patterns. Okay, all those things we will generate. And then simulation, as I told, we'll be doing the theory, theory as well as practicals. So we'll be explaining the concepts in simulation by practically implementing it in the labs. So as I told previously, why we need simulation, what happens in simulation, parallel simulation, serial simulation, how to perform simulation using QuestaSim tool. So reasons for getting simulation mismatch, how to debug the simulation mismatches, all these things we will be covering it as a part of our simulation training. So the theory and lab sessions will be done simultaneously. Okay, we'll be explaining the theory concept by practically demonstrating it in the labs. Okay, so all those things we will do it. And then level 3 and level 4 projects, they are more complex labs. Complexity will be high. Okay, so these two things you can write it as a project work in your resume. Okay, for in your resume you can write this as a project work. Write it as a project work. Okay, so the level 3 and level 4 project, you can write it as a project work in your resume. So these are test cases with higher complexity. So level 3 projects you will be having around 4k flops, and level 4 projects you will be having around 44k flops. You'll be having around 44k flops. So level 3 projects will be doing the hierarchical scan, and level 4 projects will be doing the top down scan approach. Okay, so level 3 projects will be doing the hierarchical scan, level 4 projects will be doing the top down scan. So in level 3 and level 4 projects we cover the entire flow, that is ij tag and mbist, insertion, then edt occ insertion, synthesis, then scan, then atpg, simulations, all these things we will cover it. Okay, so in level 1 and level 2 projects, we did not do the IJ tag insertion, MBIST insertion, OCC insertion and all. We have not done it, right? But in level 3 and level 4 projects, we cover everything. IJ tag and MBIST insertion, EDT, OCC insertion, synthesis, scan, ATPG, simulation, all those things we'll be doing. In the complete flow, we will cover it in the level 3 and level 4 projects. So level 3 projects is the hierarchical scan, and level 4 projects is the top-down approach. Okay. So in hierarchical scan, while discussing about the hierarchical scan, we will also cover some theoretical concepts like about scan wrappers. Okay, we'll also understand what is scan wrappers. Okay, and then like in test, x test, all those things. In test, x test, all those things we'll try to understand. Okay, when we do the hierarchical scan topic, we'll try to understand what is scan wrappers, in test, x test, so all those things, pattern retargeting. Okay, so all those things we will try to understand when we do the hierarchical scan topic. Okay, so these two are complex designs with higher complexity. So hierarchical scan level 3 projects has 4k flops, around 4k flops. Level 4 projects will be having around 44k flops. So you can write it as a project work in your resume. So this was regarding our labs. Okay, and what are all the tools which will be used for DFT? So these are all the various tools which is available for DFT in the market, but in our institute, in our course, we'll be making use of the mentor graphics tools. So for MBIS, we'll be making use of Tessent MBIS. For scan, we'll be making use of Tessent scan. For scan compression, we'll be making use of Tessent test compress. ATPG also we will make use of Tessent test compress. Simulation will be making use of QuestaSim. So at one point we need to run the synthesis. So synthesis alone we will be making use of the synopsis tool, which is nothing but the design compiler. All the other things we will be making use of the meta graphics tools in our institute. Okay, so in our course, in this particular course, we'll be covering the meta graphics tools. Okay, we'll be doing the labs with the meta graphics tools. Okay, and yeah. So who all can attend the course? So like if you're there in a final semester, a student who are in final semester, and if you're seeking DFT as your course curriculum, then you can attend a course. Okay, any new college graduate, okay, any new college graduate from relevant branches of engineering and science, you can also attend the course. Okay, and then lecturers or professors if you want to switch your career into real-time industry experience. Okay, you can also attend this course. Even working professionals from similar or other VLSI domains can attend this course. Okay, so maybe you're from physical design engineer. Now you want to get some exposure on DFT as well. Then you can attend this course. Or else you're working in IT, but you want to switch to VLSI. Then also you can attend this course. Okay, and then placement support, like we'll be having tie up with various VLSI companies, and students are entitled to placement support based on the performance in their course assignments. So during the course we will be giving you various assignments, tests, mock interview, presentation sessions, all those things will be conducted. So based on your performance on all those things you will be added into the job support group, and in the job support group the placement opportunities will be posted. Okay, mock interviews will be conducted, and then previous interview questions and preparation. So previous batches they would have attended the companies, right? They would have attended interviews. So what kind of questions was asked there? So some questions, some application oriented kind of question which is not discussed directly in our course. So those kind of questions which is asked in the interviews, that collection also we will discuss it during our course. Okay, sometimes in the interviews, previous batch students they would have experienced some application oriented questions, so which wouldn't have been covered during our course. Okay, that particular question, that particular thing, it wouldn't have been covered in our course curriculum. So we are having a collection of those kind of application oriented questions as well, and we will provide the answer to the next batch students. So the next batch students, we will provide the answer, the application oriented questions which was asked in the previous batch students. So those things we will also provide, we will also teach the answers to you, and so that you can also you will also be able to uh, like um, uh, uh, if in case you face similar kind of questions in the interview you will be able to answer them. Okay, so that also, as during our course itself we will provide you those questions as well as answers, and we will also train you to think regarding the application oriented questions as well. Okay, so that if you face a similar kind of question in the interview you will be able to answer it. Okay, and even mock interviews are also conducted which will help you to which will help you to understand what kind of questions will be asked in the interviews and how you need to answer them. So it will also give you the confidence to attend your original interviews. Okay, and we will also be giving you sample resume. Okay, we will also give you sample resume with which you can keep it as a template and you can design your own resumes. And we will also give you details about the project work, like what is our like how many flops are there, what is the clock frequency, how many clocks are there, what is the clock frequency, and then what is the compression ratio. So those kind of project details also we will share it with you. Okay, we will also share with you some project work details as well, which will be helpful to for writing your resume and as well as for answering project related questions in your interviews. Okay, and we will also try to explain how you can explain the project work in short. So if your interviewer asks you to explain your project work in short, how you can give that explanation, so that also we will provide you the training on all those things as well. Okay, so these are all the placement supports which will be providing it from the institute side. And that's it, this was regarding my demo session. And before that, before I complete, I will also want to tell you one more thing. So basically the DFT course, the DFT course, regular course, it will be for a total course duration will be first what will happen is first 2 or 2.5 months you will be having the basic training. Basic training will be done, so where you will be learning all these things like GVIM. Okay, so GVIM is actually a text editor. Okay, GVIM is a text editor, so how to work with GVIM, so you'll be learning that. And then like digital design. Okay, digital design, and then uh, linux linux and then tickle scripting. tickle scripting Okay, and then like Verilog, Verilog basics, CMOS basics. Okay, so all these things will be covered as a part of your uh, basic training. Okay, so during the basic training we'll cover all these things. Okay, so GVM, digital design, Linux, tickle scripting, Verilog basics, CMOS basics, all those things will be covered during the next 3.5 months to 4 months. During the next 3.5 months to 4 months, okay, we'll be having the DFT advanced training. DFT advanced training. So during the DFT advanced training only, whatever I told in the demo session, we will be covering that. Okay, whatever is told in the demo, whatever is told in the demo will be covered. Okay, and then like some companies they even expect you to have a small understanding on static timing analysis, STA. So I will even cover the STA basics, whatever is required to clear the DFT interviews. Okay, so like STA basics we will cover it. So STA is not a DFT domain topic, but some interviewers they expect you to have a basic idea about STA, so we'll also cover some STA basics as well. Okay, so one session we'll just take and we'll just cover some STA basics. So some kind of questions like what is actually expected for a fresher DFT interview. So some interviewers they expect it, right? So that expectation, or to meet that expectations, we will take one session and cover the basics of STA as well. Okay, so this is what will be our course. Okay, so total course will be around 5 to 6 months. Okay, it depends on the duration, so you can expect around 5 to 6 months will be the total training period, where first 2 or 2.5 months you'll be having the basic training, and then the next 3.5 months to 4 months you'll be having the DFT advanced training. Whatever we saw in today's demo session, those things will be covered. Okay, and finally after completing this complete course you will be having mock interviews, and based on your performance on your mock interviews, and also based on your performance on the various tests or assignments or presentation sessions whatever is conducted, based on it you'll be added into a job support group where the placement opportunities will be posted. Okay, so that's it for my demo. And do you have any questions from your side? Okay, so if in case you get any doubts later, okay, if in case you get any doubts later, then an individual group will be created with your VLSI Guru ID and your name. You can post your doubts, any, even if it is like non-technical or technical doubt or course related or schedule related doubts, anything you can post it in that particular group. So the respective faculty will be able to address that. Okay. Okay. So yeah, thank you all. We will end today's demo.
Okay, thank you.